In this video, we are going to look at everything that you need to know for the process of reversing the chain rule for A-level maths. Reversing the chain rule for integration is the inverse process of differentiating with the chain rule. So what we're first going to do is just think about what are our steps when we differentiate using the chain rule. So we've got our first scenario here. We're going to look at scenarios where we have some function in a bracket raised to some power. Okay, and let's look at how we differentiate it first. So dy by dx, our derivative, would be equal to, and what happens is your bracket, 3x take 1, that stays the same. Okay, so the function in the bracket stays the same. So I write that here. Then what we do next is we take our power 5 and we're going to multiply by 5. Okay, we've got the initial 4 over here and we're going to multiply that by 5 like that. And then there's one other step. We're going to go and differentiate our bracket. Okay, so we're going to differentiate 3x take 1, which gives me 3. I'm going to multiply by this as well. Okay, so I'm going to write 3 and then multiply by it like that. Okay, but the other thing we do need to write in is that our power 5 has now been reduced by 1, so it's now 4 like that. Okay, and then we can simplify our answer. So we would get 60 multiplied by 3x take 1 to the power of 4. So that is the chain rule for differentiation. Okay, that's taking me from our initial equation to our derivative. Now the reverse chain rule is going to take us in the other direction. Okay, it's going to take us from our final derivative back to our equation like that. So what we need to start considering is if we look at our answer here and then look back at the question, in that direction going to the left, what is staying the same each time and what's changing in a specific pattern? Well, hopefully what you'll notice is that our bracket, okay, our 3x take 1 is staying the same. Okay, so I'm just going to note that down. The bracket stays the same. And let's think about what changes in a specific pattern. Well, our power here is 4. Our power over here is 5. Okay, our power is increasing by 1. Okay, so our power increases by 1. And that makes sense for what we've learned previously about integration. Now what we're going to try and do is make use of this to try and integrate some expressions using the reverse chain rule. So we've got our question here, the integral of x plus 5 to the power of 3. Okay, so when we integrate using the reverse chain rule, the first thing we know that happens is that the bracket stays the same. Therefore, in my answer, we know that we are going to have x plus 5 like that. Okay, so I'm going to write that in. Then we also know that our power increases by 1 when we integrate. Okay, so if the initial power is 3, our final power is going to be 4. I know that in my final answer, we're definitely going to have x plus 5 to the power of 4. However, what we do have to consider is what happens in front of the bracket. Okay, because currently I've got a 1 written there, essentially, because it's not actually got a number written there. So we need to figure out what is that value going to be. In order to investigate this, what I'm going to consider is the fact that once I've got my final answer, so let's imagine that this was my final answer, you should be able to differentiate this with the chain rule and get back to the initial question. So what I'm now going to do is take my possible final answer and I'm going to differentiate it with respect to x using the chain rule. So we're going to differentiate the x plus 5 to the power of 4. And let's see what happens. Well, when we differentiate using the chain rule, we're going to keep our bracket the same. So we're still going to have x plus 5. We're going to multiply by our power. So we're going to multiply by 4. We're also going to differentiate our bracket. So when I differentiate x plus 5, I get 1. So I'm also going to multiply by 1. And then the power of my bracket reduces by 1. So if we initially got 4, that's going to reduce to a 3. Now if I simplify that, I get 4 lots of x plus 5 to the power of 3. Now if the x plus 5 to the power of 4 was the correct answer, then when I differentiate that, I should get exactly what the initial question was. Now, if we compare what I got down here from my differentiation, clearly these are not the same as each other. They are different. So what we have to consider next is how can I convert what I've got down here back to my initial question Well, we have a 4 in front. Over here, okay, in my initial question, we essentially have a 1 in front. So how do I get from 4 to 1? Well, you'd have to divide by 4, or in other words, you'd have to multiply by a quarter. So actually, in my answer to my integral, I should have 1/4 multiplying my brackets like that. And then, of course, we need the plus c, and then that will be my final answer. Let's have a look at another question. So here's our next question. Okay, we got 3x take 4 to the power of 6, and we need to integrate it. So let's consider what I've got written over here and think about what's definitely going to be in my answer when I integrate. Well, the bracket stays the same, so the 3x subtract 4 is definitely going to be in my answer. So I'm going to write that in here. And then it says our power increases by 1. So we have a power of 6. So if we increase by 1, we get a power of 7. So now what we need to do is differentiate what I've ended up with here. And if this is the correct answer, I should end up with the integral that I was initially computing. If I don't end up with it, we're going to have to make a bit of an adjustment. Okay, so let's differentiate my possible answer. So we're going to do the derivative of 3x subtract 4 to the power of 7. So we should be using the chain rule. So the bracket stays the same. So we get 3x take 4. We're going to multiply by our power. So we're going to multiply by 7. We also need to differentiate what's inside my bracket. So the 3x subtract 4, which gives me 3. And I need to multiply by that as well. And then my power will reduce from the 7 down to a 6. Okay, so we end up with 21 multiplied by 3x subtract 4 to the power of 6 like that. Now what I've ended up with down here is not exactly equal to my initial integral. So what I need to consider is how am I going to get from what I've ended up with down here back to my initial integral. Well, I have a 21 multiplying my brackets here, whereas in the initial question there is only a 1 in front. Okay, so how do I get from 21 to 1? Well, you have to divide by 21 or multiply by 1 over 21. So in my answer, I need to have a 1 over 21 multiplying the 3x subtract 4 to the power of 7, and then we would have plus c. Okay, so now if you go differentiate this, you will get the initial integral. Let's have a look at another scenario. So here's our next question. This one's a little bit different because we now have a 5 multiplying our bracket raised to a power. Now, there's a few ways you could approach this. We could leave the 5 there, but because it's a numerical factor of our integral, what I could do is factor this 5 out. So I get 5 and then multiplied by the integral of the 3 subtract 2x to the power of 5 with respect to x. Then what I could do is compute this integral here and then multiply my final answer by 5. Okay, that's one possible option. However, I'm just going to leave the 5 in and approach it exactly how it's written. So let's think about what's definitely going to be in my answer for my integral, making use of what is over here. So we say the bracket stays the same. So the 3 subtract 2x is definitely going to be in my answer. And it says the power increases by 1. So we have power of 5, increase it by 1, we get power of 6. Then just like we did before, we now are going to differentiate my possible answer over here and see if it gives us exactly what we started with in our integral. So I need to do the derivative of 3 subtract 2x to the power of 6 using the chain rule of differentiation. So when I differentiate, my bracket stays the same. So we get 3 subtract 2x. I multiply by my power. Okay, so I'm going to put a 6 in front like that. I also differentiate what's inside my bracket. So if I differentiate 3 subtract 2x, I get negative 2. And I also need to multiply by that negative 2 like that. And of course, when we differentiate, the power of 6 reduces by 1 to get a power of 5. Now, if we simplify, I get negative 12 multiplied by 3 subtract 2x to the power of 5 like that. So what we now need to do is compare what I've got down here with my initial question and ask myself, are they exactly the same? Clearly not. We have a negative 12 here. We've got a 5 here. So we're going to have to do something to adjust for that. So I need to consider, how do I get from negative 12 to 5? And in order to do this, essentially just go via 1. In order to get from negative 12 to 1, you divide by negative 12. in order to get from 1 to 5, well, that's fairly straightforward. We're just going to multiply by 5 like that. So always go via 1, because you just divide by the number and then multiply by your destination. So if I was writing both of these movements here as a single number that we're multiplying by, well, we'd be multiplying by 5 on our numerator, and then our denominator would be negative 12. So we're going to multiply by 5 over negative 12, which is the same as negative 5 over 12. So in my actual final answer over here, I need to write a negative 5 over 12 in front like that. Okay, and then of course plus c. And that would be my final answer. Now what we have to discuss is when can we use this method and when can't we? So in my opinion, this is the most important part of the reversing the chain rule method. Okay, you need to have a check as to whether you can actually do the reverse chain rule. If you just blindly jump in and start doing the reverse chain rule just because you see some bracket raised to a power, you're just guessing. You need to have a check beforehand. Okay, so I've got 3 questions here, and our reverse chain rule method will only work for one of the following. Now, ideally, I want to be able to figure that out just by looking at the 3 questions. But in order to investigate this, I'm actually going to carry out all 3 of these using the method that we've discussed. So if we look here, we have our bracket raised to our power. We know in our answer, we're going to have the same bracket, x cubed plus 5, but the power is going to be 1 greater. So it's going to be a power of 8 like that. Then what I do next is I differentiate this possible answer and compare it to my initial integral. So if I write out my derivative, I have the derivative with respect to x of x cubed plus 5 to the power of 8. So when I do this differentiation, I'm going to keep my bracket the same. We're going to multiply by my power, so we're going to multiply by 8. We're going to differentiate my bracket. So if I differentiate x cubed plus 5, we would get 3x squared. So I'm going to multiply by 3x squared. And then my power of 8 is going to reduce by 1 to become a power of 7. So if we simplify what we've got there, 3x squared times 8 would be 24x squared. And then we have our bracket raised to the power of 7. So let's compare what I've ended up with here to my initial integral. Well, in front, we have a 24x squared, whereas over here we have 4x. So how we get from 24x squared to 4x? Well, if you're confused with that, another way of potentially approaching this, rather than going via 1, is to set up an equation and think about what we're doing here. We're essentially asking ourselves 24x squared multiplied by something is equal to 4x, like that. So if I want to calculate this something, I need to divide by 24x squared. In other words, I need to do my destination divided by my start point. Okay, so the something I am looking for would be 4x divided by 24x squared, like that. Okay, and if I simplify that, well, we're going to end up with 1 over 6x, like that. Okay, so that is what I need to write in front of my bracket up here if this is the correct method. Okay, and then it would be plus c like that. Now let's have a think as to whether this answer makes sense given that we're using the reverse chain rule. Okay, because if we're reversing the chain rule going this way, so this is the reverse chain rule, the idea is I should be able to differentiate my answer using the chain rule of differentiation to get back to my integral. However, if we look at what we've got here, that does not make sense. You would not use the chain rule to differentiate that expression there, because we have a function of x here inside our brackets being raised to a power, multiplied by another function of x out here, the 1 over 6x. Okay, because of that, we'd have to use the product rule of differentiation. Therefore, our answer using the reverse chain rule does not make sense. So this first integral cannot be done using the reverse chain rule. Now, ideally, I want to be able to figure that out before I go through that full process. Okay, so start having a think, how could we have known that before carrying out the integral? But I'm going to have a go at the second one and see if our answer makes sense this time. So let's have a look at our second one then. So we're integrating, trying to use the reverse chain rule. So I know that my bracket is going to stay the same. So we're going to have the x cubed plus 5. And if we increase the power by 1, we're going to have a power of 8. So now what we're going to do is differentiate our possible answer, which is the same possible answer I had for the previous question. So I am just going to write in our derivative so we can get looking straight away. So this was equal to 24x squared multiplied by x cubed plus 5 to the power of 7, like that. So now let's do our comparison step. We're going to compare what we've got here with our initial integral. And as you can see, the bracket raised to the power is the same. So we're in particular focusing on what is in front. Okay, we got 24x squared. Over here, we have 5x squared. So how do I get from 24x squared to 5x squared? Well, I'd have to multiply by 5x squared, our destination, divided by 24x squared. So if I write my fraction, and then we can simplify, and the x squareds cancel, so we're just left with 5 over 24. Therefore, I have to go to my possible answer and write a 5 over 24 in front like that, and we'd have a plus c. Now let's consider whether this answer here makes sense given that we were using the reverse chain rule. Okay, so the idea is we're trying to use the reverse chain rule going in that direction. So the opposite direction, I should have to use the chain rule of differentiation. Well, if we look at what we've got here, we have a function of x here, so a bracket raised to a power, and it's multiplied by a numerical value. The 5 over 24 does not involve x, therefore we would use the chain rule of differentiation. Therefore, it makes sense to use the reverse chain rule to integrate this expression here. So this one here would be the correct one to use the reverse chain rule with. But I am just going to go through the last one just to see what happens. So looking at our last one, we have the same bracket again as usual. So x cubed plus 5, and the power is 7, so we need to increase it by 1 to get 8. And of course, again, I'm going to differentiate that possible answer there, and I'm going to get the same answer as before from that differentiation, which was 24x squared multiplied by x cubed plus 5 to the power of 7. Okay, and then we are going to compare what I've ended up with down here to my initial integral. Well, we've got 24x squared in front of the bracket here, whereas we have 3 multiplying the bracket here. So the question we need to ask ourselves is, how do I get from 24x squared to 3? Okay, so just as before, we're going to take the 3 and we're going to divide it by the 24x squared, and that's what we need to multiply by. We would have 3 over 24x squared, which simplifies down to 1 over 8x squared. So I need to write a 1 over 8x squared in front, and it will be plus c. Now let's consider whether my answer makes sense if we were using the reverse chain rule. So we're reverse chain ruling in this direction, therefore we should have to use the chain rule of differentiation in this direction, but that doesn't make sense. Okay, because we have a function of x multiplied by another function of x. That 1 over 8x squared has x in it, therefore we would need to use the product rule. Okay, not the chain rule. So therefore, using the reverse chain rule to begin with was incorrect. So this one would not be doable with the reverse chain rule. Now let's investigate how we could have figured this all out a little bit quicker. So I'm now going to go through the quickest way of checking whether we could have done these integrals using the reverse chain rule. Okay, what you're going to do is you're going to take what's inside your bracket, which is the same for all 3 of these, and you're going to differentiate it. Okay, so I'm going to do the derivative of x cubed plus 5, like that. Okay, and when I do this derivative, I get 3x squared, because I had to do the process for all 3 of these integrals at some point if you look back. Now what I'm going to do is compare this 3x squared here with what is multiplying my bracket in each instance. So we got 4x here, we got 5x squared here, and we've got 3 there. So I'm going to compare 3x squared to 4x. I'm going to compare it to 5x squared, and I'm also going to compare it to 3. And the comparison you're trying to do is you're asking yourself, in each instance, do I need to multiply by something that involves x, or do I need to multiply by something that's just a numerical value? Well, for this first one here, if we look at powers of x, we need to take a power of x from x squared down to x. Therefore, you would have to multiply by something involving x. Okay, so for this one, we cannot use the reverse chain rule. Okay, for the next one, we've got x squared and we got x squared. Therefore, we would have to multiply by something that just involves a numerical value and not x at all. So therefore, we could do the reverse chain rule for this one. Then for the last one, we've got an x squared, whereas over here, the x is to the power of 0. We don't have any x left over. So therefore, we'd have to multiply by something involving x, okay, not a numerical value. So we cannot use the reverse chain rule for that one. So the check you're doing is you are comparing this value to this one and asking yourselves, are they numerical multiples of each other? Do I need to multiply by just a numerical value? If the answer is yes, then you can use the reverse chain rule. If the answer is no, so you have to multiply by something involving your variable x, then you cannot use the reverse chain rule. That is the quickest way of checking. And you need to make this check part of your process every single time. Now let's put this check to use and have a think about a quicker way of carrying out the reverse chain rule. So here I have an equation, and this is why we're not being asked to integrate. What I'm going to say is we're going to differentiate this, okay? Because I want to investigate the differentiation steps with the chain rule again, and we're going to come up with the quickest method based off that to carry out the reverse chain rule. So when I'm differentiating, so when I'm finding dy by dx, we said our bracket stays the same. So I'm just going to make a note of that, and we're going to say bracket stays the same. We then said we multiply by our power. Okay, so we've got the initial 4, which we're going to write here, and we're going to multiply by the 5, which is our power. So I'm going to write multiply by power. Then we also multiply by the derivative of my bracket. Okay, when I differentiate the bracket, I get 3. I'm also going to multiply by that. So I'm going to say multiply by derivative of bracket. Okay, and that is specifically referring to the function inside the bracket, which in this case was the 3x take 1. And then my final step is to reduce my power by 1. Okay, so we'd have power of 4. So I'm just going to write reduce power of bracket by 1. So those are the steps for differentiating. So I'm just going to write a D here to indicate differentiation. To do integration, we're going to have to do the inverse of this process. I'm going to have to start with my final step, okay, work upwards, but every single time I am going to do the inverse. So let's try and write out those steps. So let's write an I for integration, okay, and we're going to work from the bottom step upwards, but we're going to do the inverse. So it says reduce power of bracket by 1, so we're going to increase our power of our bracket by 1, because that is the inverse. Now if we go one step higher, it says multiply by derivative of the bracket. Okay, so what's the inverse of that? Well, it's going to be dividing by the derivative of the bracket. So we're now going to move one step higher, and it says multiply by power. So what's the inverse? Well, it's going to be to divide by the power. And then let's move on to our top step, our first step for differentiation, okay, which was the bracket staying the same. Okay, so what's the inverse of staying the same? Well, it's staying the same. Okay, so the bracket is still going to remain the same. Now, in terms of the order of the steps, technically we don't have to do it in this exact order. For example, the bracket staying the same, because it stays the same, it doesn't impact anything else. We can do that whenever we want. However, the two that you do have to get in the correct order is this step up here, so increasing the power of the bracket by 1, and then the dividing by the power, because the top step influences that third step of dividing by the power. So we must do those in the correct order. But the bracket staying the same, feel free to just write that out straight away. So let's try and put these steps to use. Right, so I've got my steps written here, and I've put the bracket staying the same as the first step. I think it's just going to be a bit easier. Okay, let's try and carry out our integral using these steps. Now, before we start actually integrating using the reverse chain rule, we need to do our check as to whether the reverse chain rule is viable. So I need to take what's inside my bracket and I need to differentiate it. Okay, so if I differentiate with respect to x, 2x plus 5, I would get 2. Then if we consider the number in front of our bracket in our question, we've essentially got a 1 here. So in order to get from 2 to 1, do you need to multiply by a numerical value? Well, yes, you would have to. So therefore, we can use the reverse chain rule because you don't need to multiply by something involving x. Now let's actually try and make use of the steps written over here on the right. So first step, bracket stays the same. So we know the 2x plus 5 is going to remain the same as what we had in the initial question. It says increase the power of the bracket by 1. So we've got a power of 3. We're going to increase by 1 to 4. It then says divide by the derivative of the bracket. So if I differentiate my bracket here, if I differentiate 2x plus 5, well, I get 2. So I'm going to divide the number sort of in front of the bracket by 2. So we've got a 1 here currently. So we're going to have 1 over 2. And then it also says divide by the power. Okay, and that's in particular our new power, which is 4. Okay, so I'm going to have to divide by that as well. If we're going to divide this fraction by that 4 is going to multiply into the denominator. So I'm essentially going to end up with 1 over 4 multiplied by 2 like that. Now those final two steps, you can do them in any order. It won't end up mattering because they end up getting multiplied down here. And multiplication is commutative. And then we pretty much got our final answer. The final thing we're just going to do is write it a little bit more neatly. Okay, we got 1 over 8 and then 2x plus 5 raised to the power of 4. And of course, we do need our plus c, so let's make a little space, and we've got our plus c like that. And you can see this is much quicker than the method we were using before. Let's have a look at another question. So here's our next integral. Now, the first thing to note compared to the ones we've done, we don't seem to have a bracket raised to a power written in front of us, but we got to use indices laws because when I'm integrating, differentiating, I don't particularly like having a square root symbol. So I'm going to replace our square root symbol. Again, what we're going to write is brackets and then 3x take 5, and our power of a square root is a power of a half, and that's with respect to x like that. So we're now in position to integrate. If you want to take the 2 out of the integral, you can because it's a numerical factor. However, I'm just going to leave it in like that. Now, first thing you're going to do before trying to carry out these steps over here, we're going to check, can we use the reverse chain rule? Well, if I differentiate my bracket, I get 3. In order to get from 3 to 2, do I have to multiply by something involving x? No, you don't. You'd have to multiply by a numerical value. Therefore, we can use the reverse chain rule. So let's jump into the process then. If we follow the steps, it says bracket stays the same. So I'm going to write 3x, subtract 5, my bracket. Then it says increase the power of the bracket by 1. So we've got power of a half. So this is our first fractional power, but it works in the same way. We add 1 to it and we get 3 over 2 like that. It then says divide by the derivative of my bracket. So initially we had a 2 in front. So I'm going to divide that 2 by the derivative of my bracket, which we already did when doing our little check for our reverse chain rule. When I differentiated this, I got a 3. Okay, so I would write 3. And then we also have to divide by the power. Okay, so we're going to divide by 3 over 2. So I'm going to multiply this 3 here by 3 over 2 like that. Okay, and then it's going to be plus c. But just clean up this fraction here. You can pop it in the calculator. And we get 4 over 9 multiply 3x take 5 to the power of 3 over 2 plus c like that. Let's have a look at one more question. So this time we got ourselves a fraction. Now I don't particularly like having the x here in our denominator. Okay, so what we're going to do is we're going to start by using indices laws to rewrite this. Okay, I could write this as the integral of the 5, our numerator, multiplied by the bracket in my denominator, 1 subtract 2x. But the power is not going to be positive 3. It's now going to be negative 3 because I brought it up to the numerator. And that's with respect to x. Now let's do our check. Can we use the reverse chain rule? Well, if I differentiate my bracket here, I'm going to get negative 2. To get from negative 2 to positive 5, Do you have to multiply by a numerical value? Yes. Okay, you wouldn't need to multiply by something involving x. Therefore, we're good to use the reverse chain rule. Okay, so let's start following the steps. So we know that the bracket stays the same as our first step. So we're going to have 1 subtract 2x like that. Then it says increase power of the bracket by 1. So -3 plus 1 is -2. Be careful not to write -4, which is a common mistake. We're then going to divide by the derivative of the bracket. So I already differentiated it in my reverse chain rule check. I got -2. Okay, so what I'm going to do is take this 5 here, and I'm going to divide by -2, my derivative of my bracket. But we also need to divide by my new power. Okay, so we're also going to divide by -2 again. So I'm going to multiply by -2 in my denominator. But if we simplify that, we get -5 over 4 multiplied by 1 subtract 2x to the power of -2. That should be plus c. Don't forget your plus c's. So we're now going to look at our next scenario with the reverse chain rule, which is going to be exponentials. So to start things off, just like we did with brackets, we're going to start with some differentiating using the chain rule, okay? Because the reverse chain rule is going to be the inverse process. So we're going to have to investigate first what happens when we differentiate, which is going to allow us to integrate. So if we look at our first one here, we're going to be considering exponentials where the base is e, Euler's number. So we got y equals e to the power of x, and this is the most basic scenario where we differentiate this. This is one of the reasons the number 2.71 and so on is chosen for e. It's because e to the power of x, when we differentiate it, is equal to e to the power of x like that. Okay, so that's as easy as it gets. Now let's look at a slightly more tricky one. So we've got y equals 3 times e to the power of 4x subtract 3. So we've got a 3 multiplying in front, and we've also got a power which looks a bit more complicated. Well, our derivative dy by dx would be equal to, and what happens is the e to the power of 4x take 3 parts stays the same. And what we do is we differentiate our power. Okay, so we're going to differentiate 4x subtract 3. So I'll write that here. And that's going to give me 4. And we are going to multiply by that value. Okay, so we've got the initial 3, which I'm going to write in, and then we're also going to multiply by 4 like that. So when we simplify, we end up with 4 times 3 in front, so that's going to be 12, and then e to the power of 4x subtract 3, like that. Let's have a look at our next one then. So there's a lot more going on in the power in this one here, but let's follow the same logic. dy by dx is equal to, okay, our e to the power of 4x squared take 5x will be in our final answer, like that. But what we're going to do is we're going to differentiate our power. Okay, so I'm going to write my derivative down here. It's going to be the derivative of 4x squared take 5x, which is going to be equal to 8x subtract 5. And we're going to multiply by this value. So let's write in the initial 2 that we had multiplying our e function. And then we're also going to write in the 8x take 5. Okay, it's actually, I'm going to just shift the 2. I'm going to put it right at the front, and then in brackets, 8x subtract 5, like that. Close brackets. It's multiple terms, so we should put it in brackets. You can expand these brackets if you want, but I'm going to leave the answer like that. Right, so that's differentiating e using the chain rule. What we now need to think about is how are we going to integrate using the reverse chain rule. So remember, integrating is the reverse process. So what we're going to do is we're going to look at our answers here and think about how can we get back to our initial questions. Okay, and in particular, what we're going to consider is what is staying the same and what is changing in a specific pattern. Well, hopefully you'll notice that our base e is staying the same, okay, throughout. We've always got the e there when we're going back the other way. So what I'm going to say is that the base e stays the same. And then something else that's staying the same is our power. Okay, if you look at all of our powers, we're staying the same throughout. We have 4x subtract 3 and 4x squared take 5x. If we look back, we've got 4x take 3 and 4x squared take 5x. Okay, so the power remains the same. And this is going to be our start point to how we are going to integrate expressions involving e. So let's now just consider the most basic integral that we can get, which is the integral of e to the power of x with respect to x. Well, if we look at our answer to question 1 up here, okay, we've differentiated e to the power of x, and then we've ended up with e to the power of x. Well, if you go to our answer and you integrate that, well, what you're going to get is your initial question. Okay, so therefore the integral of e to the power of x is just equal to e to the power of x, and then of course plus c like that. Now let's look at some slightly more complicated scenarios where we're going to have to make use of what we have written down here. So we've got our integral here, which is the integral of e to the power of 3x. Let's make use of what is written over here in order to try and use the reverse chain rule. Okay, so our equals to, and the first point says base e stays the same, so we're going to still have an e in my answer. And then the second point says the power remains the same. So there's a power of 3x here, it's going to be a power of 3x in my answer. Now this is a possible answer. We're still going to have to check whether it makes sense. To do that, we're going to use the chain rule of differentiation on this and check whether we get back to our initial question. If we get back to exactly what is written in our initial question, so e to the power of 3x, then we've got our final answer. If we don't, we're going to have to make a slight adjustment. So what I'm going to do next then is differentiate with respect to x this e to the power of 3x using the chain rule. So we know that e is still going to be in there. The power remains the same. Okay, but then we differentiate our power, and when we differentiate 3x, we get 3, which is what we're going to multiply by. So we're going to get 3e to the power of 3x. Now let's do a bit of a comparison. Is what I've got written here the exact same as my integral? Well, no, it's not. Okay, in my integral, I have a 1 in front of the e to the power of 3x. Over here, we have a 3. Okay, so the question is, how do I get from the 3 I've got down here to the 1 in the initial question? Well, you'd have to divide by 3 or multiply by a third. So I'm going to put a third in front of my possible answer to get my correct answer. And then, of course, it's going to be plus c, like that. Let's have a look at another one. So here's our next integral. So let's try and carry out the steps. So the base e stays the same. And then our power remains the same. So that's looking a little bit more complicated here. We have negative 2x plus 3. And now what we're going to do is differentiate this and see if it takes us back to our initial integral. So we're going to do the derivative with respect to x of e to the power of negative 2x plus 3. So we know that the e to the power of negative 2x plus 3 stays the same. But when we differentiate our power here, we're going to get negative 2. So we're going to need to multiply by negative 2. So that's going to be my derivative there. Then what we're going to do is compare this derivative I've just found with what we had at the very start in our integral. And if we look at the numbers in front of our e function, we have a negative 2 down here, whereas we have a positive 5 up here. So the question is, how do I get from negative 2 to 5? Well, as we've discussed previously, if we're doing this by multiplication, then what we want to do is take our destination 5 and we are going to divide by our start point negative 2 like this. Okay, so we get negative 5 over 2. That is what is going to have to multiply to make this change. So in my final answer to my integral, I have to put a negative 5 over 2 in front like that. And of course, plus c. Let's have a look at another scenario. So here's our next integral. Looks a bit more complicated. We've got a quadratic power and a 4x multiplying e function. But let's try the same process then. Okay, so our base e stays the same. And then our power remains the same. So we're going to have 3x squared subtract 5 like that. We're then going to differentiate this and see what we get. So we're going to do the derivative with respect to x of e to the power of 3x squared take 5. So when we differentiate, we know we're going to have e to the power of 3x squared take away 5. Okay, but we need to differentiate our power, which would give me 6x. And we're going to need to multiply by that. So we're going to have 6x in front like that. Now let's do our comparison step. We're going to compare our derivative here with our initial question. Now if we look in front of our e function, okay, over here we have 6x, but in the initial question we have 4x. So I need to think, how do I get from 6x to 4x? Well, let's do our destination 4x divided by our start point 6x. And if we simplify that, we end up with 2 over 3. So we need to multiply by 2 over 3. So in my final answer, I'm going to put a 2 over 3 in front of my e function, and then we're going to put plus c like that. Now let's consider when we can actually use this method. So anytime you're doing the reverse chain rule, you need to have a method for checking whether it's going to work. So we've got 3 integrals here, and we need to figure out which of the 3 will the method we've been practicing actually work with. So we're going to start by carrying out the method we've been practicing, and then as I'm doing it, have a think about how we could figure out, just looking at the questions, which one it's going to work for and which one it's not going to work for. Okay, so let's carry out the reverse chain rule on this first one here. So I know in my final answer, we're definitely going to have the e to the power of 5x squared because the base stays the same and then our power stays the same. We're then going to differentiate what I've got here. So if we differentiate this, well, we would have e to the power of 5x squared, but we also have to differentiate our power, which would give me 10x, and then we're going to multiply by it to get that. But let's do a bit of a comparison here. Okay, so we got a 10x here in front, whereas in the initial question, we have a 4 in front. So how do we get from 10x to 4? Well, we'd have to do the 4 divided by 10x. So we'd get 4 over 10x, which simplifies to 2 over 5x like that. Okay, so that is what we're going to have to multiply by to make this change happen. So I'm going to put the 2 over 5x in my final answer like this, and then we're going to write plus c. Now let's consider whether this makes sense. Because if this answer is correct, I'd be able to differentiate this part here using the chain rule of differentiation and get back to the initial question here. However, if we look at what we've ended up with here, okay, we have a function of x, e to the power of 5x squared, multiplying by another function of x, 2 over 5x. Okay, so we have a product of functions of x, therefore we would need to use the product rule to differentiate and not the chain rule. Therefore, the decision to use the reverse chain rule to begin with was incorrect. Okay, we cannot do this integral here with the reverse chain rule, so I'm going to put a cross here to indicate that. Now let's look at the next one. So if we're using the reverse chain rule, I know that the e to the power of 5x squared is definitely going to be in my answer. Then what we're going to do is differentiate this here and compare it to the initial integral. So I've already spoken about the derivative because it's the same format, this integral, as the previous question we did. And the derivative was 10x multiplied by e to the power of 5x squared. Then we're going to do our comparison step. So here we've got 10x multiplying our e function. Here we've got 4x. So how do I get from 10x to 4x? Well, let's do division. We'll do 4x divided by 10x, which simplifies to 2 over 5 like that. Okay, so what I'm going to do is put this 2 over 5 in my answer, multiply our e function, and then it should be plus c. Now let's check whether this answer makes sense. Would I have to differentiate this using the chain rule to get back to my initial integral? Well, yes, you would, because we've got a function of x involving e to the power of 5x squared. However, 2 over 5 in front is a numerical value. That does not involve x, therefore we can use the chain rule to differentiate. So therefore our decision to use the reverse chain rule was correct. This is the one you can use the reverse chain rule for. But let's just investigate the bottom one to see what happens. Right, so the last one, we know in our answer we're going to have the e to the power of 5x squared, as it's the same format as the previous questions. If we differentiate this, I get 10x times e to the power of 5x squared. And then we're on our comparison step. We're going to compare the 10x to the 4x squared multiplying up here. So we need to figure out how to get from 10x to 4x squared. Well, let's do our division, and that would be 4x squared divided by 10x, which if I simplify, we end up with 2x over 5. Okay, so that's what we need to multiply by to make this change happen. Well, let's put that in front of my final answer. So 2x over 5 multiplying e to the power of 5x squared plus c. And let's just investigate then. Does this answer make sense? If I were to differentiate this using the chain rule, would I get back to my initial integral? Well, we've got a function of x with the e here, multiplying another function of x, the 2x over 5. So therefore, you shouldn't be using the chain rule to differentiate. We'd have to use the product rule. Therefore, using the reverse chain rule to begin with was a wrong decision. Okay, so we cannot integrate this using the reverse chain rule. Now let's consider how we could have figured out the second integral was the right one to use the reverse chain rule on. without going through the whole process. Right, so the check we're going to do is we're going to consider what's the same between all of them, which is our power 5x squared. Okay, during the process for carrying out the reverse chain rule, I differentiated that power of 5x squared every single time. So let's just write out the derivative here, just so I can see it clearly. So our derivative was 10x. Okay, and what you're going to do is you are going to compare this derivative that we've got here with what is multiplying our e function each time, the part that's actually different between these questions. So we've got a 4 here, we've got a 4x here, and we've got a 4x squared there. Okay, so what I need to consider is how do I get from the 10x over here to each of those red bits I've circled. Okay, so how do I get from 10x to 4? How do I get from 10x to 4x? And finally, how do I get from 10x to 4x squared? And the question you're going to ask yourself is, do I need to multiply by a numerical value or something involving x? If it's a numerical value, then you can use the reverse chain rule. If it's something involving x, then you can't. Because what you'll find is when you go differentiate your integral at the end to check your answer, okay, you'd have to use the product rule, which doesn't make sense. Okay, so if we're trying to go from 10x to 4, well, we need to remove the x. So clearly we're going to have to multiply by something involving x. So therefore, we don't use the reverse chain rule on that one. Now, the next one, the powers of x are the same. So therefore, we'd have to multiply by a numerical value. So we can use the reverse chain rule. And then the final one, we have x, and we have x squared. So we clearly have to multiply by something involving x. Therefore, we cannot use the reverse chain rule. So it's only the middle one, which we can use the reverse chain rule for, and that is what we established before. So just make sure you always do this check before you jump into using the reverse chain rule. So now let's practice using this check and have a think about the quickest way to integrate a function involving e using the reverse chain rule. So to come up with our quickest way of integrating, we're just going to have to consider differentiation again and clearly write out every single step I do whilst differentiating. Okay, so to get dy by dx for this equation here, we said our base e stays the same. Okay, so base e stays the same. Our power 4x take 3 stays the same. So I'm going to note that here. So power stays the same. And there's one other step that we do. We differentiate our power, which in this case gives 4, and we multiply by this value. Okay, so we'd write in the 2, and then we would multiply by 4 like that. And you can simplify it to 8, but I'm just going to leave it like that and make a note of the step I just did. Okay, so we multiply by the derivative of the power. So that's differentiation. We're now going to consider integration. Okay, for integration, we're going to have to do the inverse of what is written here. So I'm going to write I to represent integration. Okay, and what we're going to have to do is start with our final step for differentiation, okay, and do the inverse of it. Okay, so it says for differentiation, we need to multiply by the derivative of the power. Well, what's the inverse of that? Well, it's going to be to divide by the derivative of the power. Now let's move one step higher. Okay, so this one here. Well, it says power stays the same. What's the inverse of staying the same? Well, it's staying the same. Okay, so the power is still going to stay the same. And then if we move one step higher, well, it's very similar. It says base e stays the same. So the inverse of that would be base e staying the same. Now, for staying the same steps, we can do those first. Okay, they don't influence any of the other steps, so that's fine. Okay, and actually, I think it's going to be a bit easier if you focus on these two steps first and then do the dividing. So let's practice using these steps. So we've got our integral, and I've got my reverse chain rule steps on the right over here. Okay, but what we're going to start by doing before we do those steps is we're going to do our reverse chain rule check. So we're going to differentiate our power. So if I differentiate negative 4x with respect to x, I would get negative 4. Then we're going to compare this value here to the value in front of our e function in the integral. Well, in front I've got a 1. Okay, to get from -4 to 1, do you need to multiply by a numerical value? Yes, okay, it wouldn't involve x. Therefore, we're good to use the reverse chain rule. Okay, so let's start carrying out our steps then. So step 1 says the base e stays the same. So I'm going to write equals to, and then I'm going to write e. And then it says the power stays the same. So that -4x in the power must remain in my final answer. Then it says we're going to divide by the derivative of the power. Well, we've already differentiated -4x as part of our reverse chain rule check. We got -4. So what I need to do is go to the 1 that's multiplying in front of our e function in the integral, and I need to divide it by -4. Okay, and then it'll be plus c. And the neatest way of writing it would be -1/4 e to the power of -4x plus c, like that. Let's have a look at another question. So here's our next integral, and this one looks a little bit more complicated because we now have e in the denominator, which is not what we've dealt with so far. So first off, I want to rewrite my fraction so that e is no longer in the denominator. So let's just consider an easier scenario you should be familiar with. So let's say we had 5 over x squared. Well, you should know that this rewrites to 5 multiplied by x to the power of -2. So we brought the x up to the numerator, but what we've had to do is multiply our power by -1 in order to make that happen and get an equivalent expression. So let's deploy the same logic here. Our numerator is still 5, so I'm going to write 5, and that's going to multiply e to the power of something. Okay, it's going to be our initial power in the denominator here, multiplied by -1. So I'd write -1 times 1 subtract 3x in brackets like that. Okay, with respect to x. And we need to put our integral symbol in because we haven't actually integrated yet. Now I'm going to simplify my power. So it's going to be the integral of 5e, and then multiply everything in the brackets by -1. So we would get -1 plus 3x with respect to x. Now let's carry out our check as to whether we can use the reverse chain rule. Okay, so what we do is we go to our power, -1 plus 3x, and we're going to differentiate it. If I differentiate -1 plus 3x, well, that is going to give me 3. Well, if I compare this 3 to what is initially multiplying our e function, which is 5, to get from 3 to 5, you'd have to multiply by a numerical value. Okay, they're numerical multiples of each other. You wouldn't have to multiply by something involving x. So we're good to use our reverse chain rule. So let's now try and carry out our steps of our reverse chain rule. Well, we'd write equals to, and our first step says the base e stays the same. Step 2 says the power stays the same, so -1 plus 3x. Then step 3 says divide by the derivative of the power. Well, we've already differentiated the -1 plus 3x. It gave us +3. So I'm going to divide the 5 that we had initially here by 3, and that gives us our answer with a plus c on the end. Let's have a look at another scenario. So here's our integral, and we're going to start with our reverse chain rule check. So we're going to take our power, 3x squared take 4, and we're going to differentiate it. So if I differentiate 3x squared, subtract 4, well, I would get 6x. But in order to get from 6x to the 2x multiplying our e function, would we have to multiply by a numerical value? Yes, we would, because the powers of x match, so we wouldn't have to multiply by something involving x. Therefore, we can use the reverse chain rule. Okay, so let's have a go at carrying out my steps then. So our first step says that our base e stays the same. So I'm going to write my e in. And then it says that the power stays the same. So we're going to write 3x squared take 4 as the power. And then it says divide by the derivative of the power. Well, we just differentiated the power during our check. We got 6x. Okay, so what I'm going to have to do is take the 2x that we had initially, and we're going to divide by the 6x like this. And then it would be plus c. Then all we need to do is just simplify what is written there. Okay, because 2x divided by 6x leaves me with 1/3 e to the power of 3x squared take 4 plus c, like that. Let's consider one more scenario for e. So here's our scenario, and this one looks a lot more complicated because we now have a bracket raised to a power, and it's being multiplied by a function involving e. Well, bracket raised to a power, we haven't been concentrating on that in this section, but we dealt with this scenario in the previous section. Okay, our previous type of scenario that we need to investigate for the reverse chain rule. In that scenario, to check whether we could use the reverse chain rule, what we would do is we would take the function in our bracket, so the 5e to the 2x subtract 4, and we would differentiate it. Okay, so let's do that check. If I differentiate this, well, the negative 4 is just going to differentiate to 0 because it's a constant. And then my e term, well, we'll have the e to the power of 2x staying the same. Then we'd differentiate our power to give me 2. And I'd multiply the 5 by the 2 to get 10 like this. Then in that check for the bracket scenario, we would then compare what I've got written here to what is in front of our bracket up here, multiplying it. Okay, we have e to the power of 2x. So in order to get from 10e to the power of 2x to e to the power of 2x, do we have to multiply by a numerical value or something involving x? Well, the e to the power of 2x's match. Okay, the only thing that's different is the 1 in front here, whereas we got a 10 over here. So we would have to multiply by a numerical value. Therefore, we could use the reverse chain rule. But instead of using my steps for doing e, we're going to consider our steps for doing brackets raised to a power. So I've got my steps here. Let's carry them out. So step 1, it says bracket stays the same. Okay, so the 5e to the power of 2x subtract 4 is definitely going to be in my bracket at the very end. Then it says increase the power of a bracket by 1. So we've got 4 here. So we're going to put a 5 over here. Then it says divide by the derivative of the bracket. So we're going to have to differentiate what's in my bracket, which we already did during our reverse chain rule check. And that gave us 10e to the power of 2x. Okay, and I need to divide by that. Okay, so we're going to take the initial e to the power of 2x in front of our bracket. Okay, and we're going to divide by 10e to the power of 2x. However, final step also says divide by the power. Okay, so we've got a power of 5. So that's going to multiply into my denominator like that. And of course, we would have plus c. We then need to simplify. Well, the e to the power of 2x in the numerator and denominator will cancel. Okay, so we're just going to be left with 1 over 10 times 5, which is 50. So our final answer is 1 over 50 times 5 e to the power of 2x, subtract 4 to the power of 5 plus c, like that. Now let's consider when the base of our exponential is not e. So we've now got some equations where the base is no longer e. Okay, it's some other number. We got 5 in the first one, we got 4 in the second one. However, before we get onto integration, we need to just consider differentiation. After all, integration is the inverse process. So let's just remind ourselves of some derivatives you should know. So if you have y equals a to the power of x, then dy by dx would be equal to the a to the power of x, that was in the initial equation, multiplied by ln a. Okay, so where a is the base of our exponential. So both of these values here should be the same, and there'll be known numerical values. Okay, so a is a constant. But let's look at the slightly more complicated scenario, which is that y is equal to a to the power of kx. Well, then dy by dx would be equal to, and we would have k multiplied by a to the power of kx ln a. Okay, so what's changed? Well, our power has remained the same throughout. Okay, however, the big difference between this derivative and the one above it is now we have this k multiplying by a to the kx ln a that we have to account for as well. So let's just apply these derivatives to our equations over here, just so you're happy with a numerical example. So if we have y equals 5 to the power of x, this seems to most resemble this top one up here. Okay, so our derivative dy by dx would be equal to, and it would be 5 to the power of x ln 5. Okay, because our value of a is our base is 5, so that's going to be a in my final answer, like that. Now for the second one, perhaps it more resembles the bottom version that I've written out here, the slightly more complicated version. So we would have dy by dx is equal to, so our value for a this time would be the 4, and our value for k would be the 2 multiplying the x. Okay, so now we can write out my derivative. It would be k, which is, we said, equal to 2, multiplied by our initial exponential, which was 4 to the power of 2x, and then ln a, and we said a was the 4. Okay, so that would be my final answer. So let's say we had something slightly more complicated where we had y equals 7 times 4 to the power of 2x instead. So we've got this exponential up here, but we've now multiplied by 7. Okay, so 7 is a numerical value. It doesn't involve x. This doesn't make the differentiation any more difficult. Okay, our dy by dx is just going to be the same as what we've got here, but we're going to multiply by 7. Okay, so when I multiply by 7, this 2 is going to become a 14. So we get 14 times 4 to the power of 2x ln 4 like that. Now what we're going to do is make use of these rules here to integrate instead. So we've got our integral here. We're doing the integral of 2 to the power of x with respect to x. Now if we look at our derivatives, this here seems to resemble more our top one up here, okay, because in our power we just have x. X isn't being multiplied by a number other than 1. So I'm just going to take off this bottom one, okay, because what we're going to do is try and make use of this top one to come up with our answer for the integral. Okay, so if we know that differentiating y equals a to the power of x gives a to the power of x ln a, well, that statement also tells us an integral. If we integrate our derivative with respect to x, we're going to get back our initial equation. So I can write that a to the power of x ln a integrated with respect to x is going to be equal to a to the power of x, our initial equation. Now you might be looking at this and thinking this doesn't entirely match with the integral I'm working with in this question because we've got this ln a over here. But remember, a is a known value. Okay, it's a numerical value. So ln a is a constant. So what this allows us to do is to go to our integral and we can divide by ln a. And then all we need to do is divide by ln a to get our answer to our new integral. Okay, because dividing by ln a on the left-hand side is going to cancel out this ln a. So we're just left with a to the power of x with respect to x is equal to, and it would be a to the power of x divided by ln a like that. Okay, so now my integral down here matches very nicely with the one I'm actually trying to compute. Okay, Ra is equal to 2. Okay, our base. Now we can write out our answer. It's going to be equals to, and then we're going to write out this fraction down here with our value of a subbed in. So it'd be 2 to the power of x divided by ln 2 like that. And of course, we would need our plus c. Let's have a look at another one. So let's look at our next integral. Okay, so this one's a bit more challenging. We've got our base as 3, so that's going to be a in my equations over on the right. However, our power now has a number other than 1 multiplying by x. Okay, we've got 2 in there. But also we have a number multiplying our whole exponential term, which is the 5. Now, to make life a bit easier in this question, what you could do is you can factor that 5 out because it's a numerical factor. So we would get equals to, and then I'd write 5, and then our integral symbol, and then 3 to the power of 2x with respect to x, like that. Okay, and it might just be a bit easier to approach now that we've written it like that. So let's just compare our integral here, which we have to calculate and then eventually multiply by 5, with our two equations over on the right here. Now it seems that this integral far more resembles what's going on in the bottom equation, okay, because we have 3 to the power of 2x, okay, so we have something other than 1 multiplying x in our power. So let's make use of this bottom one and think about what integral I can obtain from this. Well, if we know differentiating a to the power of kx gives this result here, then integrating this result here should get us back to the a to the power of kx. So let's write that out. The integral of k times a to the power of kx ln a with respect to x is equal to a to the power of kx. And of course there'll be a plus c, but let's not worry about that for now. Now if we look at this integral that I've got written here, this does not completely resemble the integral that I am now trying to compute. Okay, so let's manipulate our general format down here to get it in a more favourable format. So what we're going to do is we're going to try and remove the ln a, and we're going to try and remove the k. Okay, because in my one it's just 3 to the power of 2x. Well, k is a constant, okay, and ln a is a constant. So therefore we can divide by both of them and then just divide our answer to our integral by both of them as well. And it's still a valid statement. Okay, so what I'm going to do is divide by k and divide by ln a on both sides. So divide by k, divide by ln a. So in my integral, the k and the ln a are cancelled out and we're left with a to the power of kx with respect to x is equal to, and then we would get a to the power of kx divided by both bits. Okay, so they're going to multiply together in our denominator, so we'd have k ln a like that. And of course, you'd have your plus c. Now let's try and make use of this then. So in my integral that we're working with, our value of a is going to be our base, which is the 3, and our value of k is going to be what's multiplying x in our power, which is going to be the 2 here. Okay, so we've got the values we need. I just have to make use of them by using my general format for my integral that we've got written down here. Okay, so don't forget about the 5, okay, because it's easy to forget. We're going to multiply our answer by 5 at the end. And then for my integral, what I would get, I'm going to put it in brackets. We'd have a to the power of kx, so that's going to be 3 to the power of 2x when I sub in my a and my k. And in my denominator, I would have k ln a, so that's 2 ln 3 like that. Okay, and then of course plus c. Now that 5 can multiply up to the numerator, so I would have 5 times 3 to the power of 2x over 2 ln 3 and then plus c. Please don't multiply the 5 and the 3 together because the 3 is raised to a power. You must do indices before multiplication. Let's have a look at a scenario which is slightly more difficult. So here's our final integral. So we've got 2 to the power of 3x plus 4. So now we've got something being added in the power as well, which is a bit different to the general formats I've got written over on the right. So I want to manipulate this first to get that 4 out of there. So I'm going to write equals 2 and then our integral symbol. And I need to think about how I can split this term up. Okay, well, when considering adding with powers, we need to think about multiplication. We're going to write this as a product of 2 terms. And both of those terms are going to have a base of 2, like the base of the exponential we've got over here. Now, when we multiply terms with the same base number, we add the powers. Therefore, I can write one power as 3x and the other power as 4. Because when we do 3x added to the 4, we get the 3x plus 4 in our initial power. Okay, so we successfully decoupled the 3x and the 4 in the power. I just need to write in my dx. And of course, 2 to the power of 4, well, that's just equal to 16. So I'm going to write times 16. And now this question looks a lot like the one I just did. Okay, what we can do is factor out the 16 because it's a numerical value. Okay, it doesn't involve x. So I can write 16 and an integral symbol and then 2 to the power of 3x dx. And now we're ready to make use of the result at the bottom here. Okay, so let's just identify what is our a. Well, that's our base, which is 2. What is our k? Well, that's what's multiplying x, which is 3. Okay, so now let's try and substitute into our general format. Well, I've got 16, and then I'm going to open brackets. I've got a to the power of kx, so it's going to be 2 to the power of 3x, like that. Okay, so essentially the initial exponential. And then divided by our value for k, which is 3, multiplied by ln of the base of our exponential, which is 2, like that. And of course, plus c. Then the final thing I can do is multiply the 16 up to the numerator, and then I've got myself the final answer in this case. Now let's have a look at questions where we're going to have to make use of the natural logarithm. So we're now going to look at how we can integrate and use the natural logarithm to help. So let's start with some derivatives as usual. So if y is equal to ln x, then dy by dx is just equal to 1 over x. That's a standard derivative that you should know. Let's have a look at the second one. Okay, this one's a bit more complicated. Now, when we're differentiating in these more complicated scenarios, the idea is the 3x subtract 2 is going to be your denominator. And then what you have to do is differentiate the 3x subtract 2 to get the numerator. So if I differentiate 3x subtract 2, I get 3. So that's going to be my numerator. And that's my derivative. Let's look at the next one. This one, we got a 2 multiplying in front as well. So let's write dy by dx is equal to, okay, and the 3 take 4x, that is going to be my denominator. And then we're going to differentiate that to get my numerator. So that would give me negative 4. And then we just need to remember to multiply by 2. So I'd write 2 times like that. And then we can simplify this. Okay, it would become negative 8 in the numerator. So I'm going to put the negative at the front, write 8 in the numerator, and then 3 subtract 4x in the denominator like that. Now let's look at a generalization. So if we have y equals the natural logarithm of some function of x, so that's essentially just what's in our brackets each time, then dy by dx is going to be equal to a fraction where the denominator is the f of x, and then the numerator is the derivative of that. So in terms of function notation, I would write f dash x like that. Now let's start thinking about integrating, and let's use this generalization here to help come up with an integral. Okay, because if I am differentiating going this way using the chain rule, going back the other way, I'm integrating using the reverse chain rule. Therefore, the integral of this fraction here, so the derivative of the function of x divided by the function of x with respect to x, should be equal to ln of f of x, like this. And this provides us with a standard result that we can use to integrate fractions. And our answer is going to involve the natural logarithm. So we're not practicing integrating the natural logarithm right now. We're going to use it to help us integrate fractions. And the format of our fraction is such that the numerator is the derivative of the denominator. Or it could be a numerical multiple of it. Because if I was to go to my numerator, and let's say we multiply by k, okay, then all we'd need to do to adjust is we would need to put a k in front of our natural logarithm function. So we would get this here. For example, if I look back at my third derivative, if we were to integrate this fraction here, well, the numerator isn't a perfect derivative of the denominator because we multiplied by this too. But once we integrate this fraction here, if you look back at the initial question, which would be our answer, you can see I've got that 2 in front, which represents what multiple 8 is of our actual derivative of the denominator. Now let's just take a look at the most simplistic integral that you can get for this scenario. So the integral of 1 over x. Well, you don't even need to refer to this over here to help. You can refer to our first derivative, which shows that the derivative of ln x is 1 over x. Therefore, the integral of 1 over x would be ln x. Okay, so I would write ln x. And of course, it should be plus c in both cases with that and my generalization over here. Now, you might be asking, why for the 1 over x? Why can't I just write that as x to the power of negative 1? Well, the problem is, if we then add 1 to our power, okay, we're going to get a power of 0, and then we can't divide by 0. That's undefined. So that result of adding 1 to the power and dividing by it, that works for all powers that are not negative 1. Okay, so you're going to be looking for fractions where the denominator is raised to the power of 1. Okay, so for example, if we look back at this fraction up here, okay, my denominator is raised to the power of 1. Therefore, if I tried to rewrite it using indice laws, I would get 3 multiplied by 3x take 2 to the power of negative 1. And we don't want a negative 1 power. Okay, if this power in the denominator was anything other than 1, then yes, we could try and use indice laws, which we practiced earlier on in this video when considering our bracket scenario. However, there is one extra thing we do need to include in our integral that I haven't mentioned yet. Okay, and that is we can't actually use normal parentheses. Okay, we cannot use these standard brackets I have here. We actually have to take them off. Okay, we have to use modulus symbols. So I must put modulus symbols around the function in my natural logarithm. Now you might be asking why. Well, I'm going to go through the full explanation later on in the video. Okay, we're going to practice using this result first. However, one of the simple explanations is that you can't do the natural logarithm of a negative value. Okay, so if we look back at my integral for 1 over x, okay, we're going to put modulus symbols around my x, okay, because I can't just substitute a negative x value in if we don't have our modulus symbols, because the natural logarithm of a negative number is undefined. Therefore, I'm going to put modulus symbols in, and later in the video we'll discuss why this still gives the correct result if, let's say, we try to calculate the area under a curve, which is what integration is used for. Now let's try and make use of this result. So here's our first integral, and we're going to run through a check as to whether we can use the natural logarithm, which involves differentiating your denominator and checking if the numerator is a numerical multiple of it. Because if we look at our result, we need the numerator to be the derivative of the denominator or a numerical multiple of it. So if I differentiate x subtract 3, I would get 1, which perfectly matches with my numerator. Therefore, my final answer is going to be the natural logarithm of the modulus of my denominator, x subtract 3, and then, of course, plus c like that. And we wouldn't need to write any other value in front other than 1 because the denominator, when differentiated, gave exactly equal to the numerator. So let's look at our second one. So let's do our check for the reverse chain rule, which involves differentiating my denominator. So if we differentiate 7x take 3, I would get 7. And then if we compare this 7 I've got here to my numerator, okay, are they numerical multiples of each other? Yes, they are. Okay, in order to get from 7 to 2, we would have to multiply by the 2 divided by the 7, like that. Okay, we're going to make use of this in our answer. Now, our final answer then is going to be equal to, and we're going to do the natural logarithm of the modulus of the 7x subtract 3. However, to account for the fact that the numerator is not a perfect derivative of the denominator, we are going to have to multiply by the 2/7 we have here to ensure that we get the correct numerator. Let's have a look at my third one. So let's do our check, which involves differentiating the denominator and comparing it to the numerator. So if I differentiate my denominator, we get -4. Then let's compare it to my numerator, which is 10, but don't forget about the negative sign there. So my numerator is going to be -10. Well, to get from -4 to -10, you'd have to multiply by a numerical value. So we can use our natural logarithm. And what we'd have to multiply by would be the -10 divided by the -4, okay, which simplifies down to 5/2. Okay, so that's going to be involved in my answer. What I can then do is go back to our question and write the natural logarithm of our denominator in modular symbols, so 3 subtract 4x, like that. And then we're just going to pop the 5/2 in front like that. And of course, all my answers should have plus C's. I forgot it up here, and we should include it down here as well. Let's have a look at a follow-up question to this last one. So it says, hence calculate, and we have a definite integral this time because we've got our limits. Now it says hence because in the previous question, which I've got written over here, we've already integrated this fraction. So let's make use of that. Okay, I'm going to write equals to, and I'm going to put square brackets. I'm going to write in my integral, so 5/2, and it's ln of the modulus of 3 subtract 4x. And then our limits are 3 and 2. So let's start substituting my limits in. So I would get 5/2 ln, and it'd be the modulus of 3 subtract 4 multiplied by my upper limit, which is 3. And then I close my modular symbols. And then I'd write subtract, and then 5/2 ln, and then the modulus of 3 subtract 4 multiplied by my other limit, which is 2. Okay, so I'm going to sub that in there. And we'll close our modular symbols. Now let's have a go at simplifying. So we'd have 5/2 ln, and then inside my first modular symbols here, 3 subtract 12 would give me -9. Close my modular symbols, and then subtract 5/2 ln, and then for this one, 3 subtract 8 would give me -5, like that. And of course, these negative numbers, if we didn't have our modular symbols, it would be undefined because we can't substitute a negative number into the natural logarithm of x. Now let's simplify what's in my natural logarithm, because we'd have the 5/2, it'll be the natural logarithm, and the modulus of -9 is +9. Now once I write that in, we can either just drop the modular symbols or replace them with normal parentheses, and then subtract 5/2, and then the natural logarithm, and this time it would be +5. Okay, so that's how you deal with limits and the modular symbols. Now we can simplify because usually you're expected to give your answer in the most simple form. Well, 5/2 is a common factor, so I can factor that out. So we'd have ln 9 subtract ln 5. I don't technically need to write the parentheses around the 9 and the 5, so that's fine. And then finally, we'd have 5/2, and then we could use log laws, okay, and we could divide the 9 and the 5 because the logs are being subtracted. So we get ln of 9/5 like that, which would be my final answer. Now let's have a look at some trickier integrals. So let's look at our next one, and let's do our usual check of differentiating my denominator. So the derivative of x squared take away 1 would be equal to 2x. And then let's compare this to my numerator. So would I have to multiply by a numerical value to get from 2x to 7x? Well, yes, you would, because the powers of x match. So 2x to 7x. Well, to figure out what we multiply by, we're going to do the 7x divided by the 2x, okay, which simplifies down to 7/2, which is going to be part of my final answer. And I can now write out my final answer, which is going to be the 7/2 first, and then the natural logarithm of the modulus of my denominator, x squared subtract 1. Okay, so the fact that we had x in our numerator doesn't change things. We still do the same check and see if it's a numerical multiple of the derivative of the denominator. Let's have a look at the next one, which brings e into play. Okay, so it looks more complicated, but we've got a fraction. Okay, and importantly, our denominator is raised to the power of 1 again, like all the questions I've been doing, because in this scenario, we're not going to want to write it as a negative 1 power. So let's do our usual check of trying to see if we can use the reverse chain rule with the natural logarithm by differentiating my denominator, so e to the power of 2x subtract 3 plus 2. And let's see what we get. Well, the plus 2 is a constant, so when we differentiate that, we get 0. Now, for our e function, well, it's going to be e to the power of 2x.
Subtract 3.
Power doesn't change. However, we need to differentiate our power, which gives me 2, and I need to multiply by it, like that. Okay, and if we compare what we've got here with our numerator, well, you'll see they're numerical multiples of each other. The e to the power of 2x subtract 3 is common. Over here, we've got a 2. Up here, we've got a 1. Okay, so the question we're essentially asking ourselves here is how do we get from 2 to 1? Well, we'd have to multiply by a half. So now we can write out my final answer. Okay, it would be equals to 1/2, which is what we just established down here, multiplied by the natural logarithm of the modulus of e to the power of 2x subtract 3 plus 2, like that. And of course, we need our plus c's, which I forgot up here. However, in this one, we actually don't need the modulus symbols. As to why, well, when you don't need the modulus symbols, it's because what's in our natural logarithm is always going to be positive, regardless of which x value we put in there. And if you have e to the power of anything, whatever value you put in that power, it's going to come out as positive. Because if we consider the graph of e to the power of x, like this, okay, you can see it is always positive. The only way a graph involving e is going to become negative is if we translate it downwards or we reflect it in the x-axis, which isn't occurring from the e to the power of x to the e to the power of 2x subtract 3. Therefore, that part's always positive. And then we've also got a plus 2, which isn't going to suddenly make it negative. So technically, we're allowed to drop the modulus symbols for this one. So we are allowed to write 1/2 of the natural logarithm, and then in parentheses, e to the power of 2x subtract 3 plus 2, close brackets, plus c, like that. Okay, and that is a valid answer for that specific question, because what is in the natural logarithm will always be positive, regardless of which x you put in. However, you could have left the modulus symbols if you wanted to. Let's have a look at another one. So here's our integral, and actually this one looks a bit more straightforward, but what we'll find, there's actually multiple ways of presenting our final answer, which is what we need to discuss. So one potential way of approaching things is taking our denominator, 3x, and differentiating it, and checking, can we use the reverse chain rule? Well, if I differentiate my denominator, I get 3. Well, if I compare the 3 to the 1, well, to get from 3 to 1, you'd have to multiply by numerical value, and that numerical value would be 1/3. So therefore, our final answer could be equals to, and then it would be 1/3 of the natural logarithm of the modulus of 3x, my denominator, and we're going to write plus c like that. However, I do want to think about another way we could have approached this question. Okay, so I'm just going to take off this derivative, and my other way of approaching this is to start by factoring out 1/3. And we can do this because 1/3 is a factor here. Okay, it's multiplying into the 1/x, so I would have 1/3 integral symbol 1/x dx, like that. Okay, and what I can do now is recognize that the integral I've been left over with here is sort of a standard integral that you need to know. Okay, the integral of 1/x with respect to x is just the natural logarithm of the modulus of x. So I could write our 1/3 and multiply by the result of my integral, which is ln of the modulus of x. And then I'm going to write plus and my constant, but instead of writing c, I'm just going to write d. The reason being, these constants are going to be different because we've got different expressions here. Now you might be thinking, oh, they look different, surely one's correct, one's not. Actually, they're equivalent, they're just going to have different constants, hence why I've written different letters. Now as to why, let's go back to this first one here, and let's try and manipulate our 1/3 of the natural logarithm of the modulus of 3x. Well, using log laws, if we have multiplication in here, we can write this as the sum of two logs. Okay, so I'd have my 1/3, and I'm going to open brackets, and would have a natural logarithm of the first number in my product here, the 3, which I don't have to put modulus symbols around because 3 is positive, so I'm just going to put normal parentheses. And then that would be added to the natural logarithm of the other value in my product, which is the x. Okay, so I would have to keep modulus symbols here, and then close brackets like that. Now, if I expand my brackets, I get 1/3 ln 3 plus 1/3 ln of the modulus of x. So if we now look at what we've got, this part here matches with this part here from my other answer. Okay, the only difference, we have the 1/3 ln 3. Well, 1/3 of ln 3 is a constant. Okay, this here is a fixed numerical value. If you put it in the calculator, you're going to get a decimal. So the idea is I could combine it with the c, okay, to get a different constant, which is going to be the plus d. Okay, so then essentially I'd end up with the exact same result as I had down here. So if we write in our changed answer for the 1/3 ln of the modulus of 3x, I could write this entire expression that I've got up here. Okay, so I would be writing 1/3 of ln 3 plus 1/3 of ln of the modulus of x. And of course we'd have our plus c. And then the idea is this plus c can be combined with the third ln 3, okay, to make another constant, okay, which I'm going to call d. So we would have the 1/3 of ln of the modulus of x. And then for the red parts, I would replace that with a plus d, which would be equivalent to the constant that I had down here earlier on. Now let's just have one final discussion about when we can use this process. Okay, so we have 3 fractions, 3 integrals, and it says the method will only work for one of the following. Well, if you look at all of the integrals, the denominators are all raised to the power of 1, so therefore we can't use indice laws. We're going to have to potentially consider our natural logarithm. And remember, our check is to differentiate my denominator, which is common to all 3 questions. So 2x squared, take away 3. If I differentiate this, I get 4x. And all we need to do is compare this 4x here with our 3 numerators and figure out which one is a numerical multiple of it. Well, it's going to be the one with the same power of x. Okay, so it's going to be this one up here. So this is the only one I can use the process for. But as you can see, all these fractions do look quite similar. Okay, so make sure you do this check. Don't just assume because it's a fraction with the denominator raised to the power of 1 that you can jump into this process. You do need to do the check. So let's have a think about why we need the modulus symbol in our answer. To do that, we're going to consider the integral of 1 over x with respect to x. And we're going to consider this integral for all values of x. So x is a real number. So I'm going to say x is an element of the real numbers. However, x cannot be equal to 0. The reason being, when I substitute 0 into here, we're going to get 1 divided by 0, which is undefined. However, any other x value, positive or negative, you can substitute into 1 over x, and you do get a defined result. Now let's try and integrate this. Now if we check our denominator, okay, which is x, if we differentiate x with respect to x, we get 1, which perfectly matches my numerator. Therefore, the answer should be the natural logarithm, and then we're going to put x, our denominator, and we're just going to put it in parentheses like this, okay, so no modulus symbols yet. And then, of course, it is plus c like that. Now let's consider whether this answer makes sense. Because we said that we can substitute any value of x apart from 0 into 1 over x. However, if we substitute a negative value into our natural logarithm, it's going to be undefined. Okay, which doesn't make sense. Because remember, integrals work out the area under the curve. So if I was to sketch the graph of 1 over x, it would look a bit like this. And clearly for our negative x values, which are over here, okay, there is area under the curve to find. Okay, because if I was to pick some negative x values, for example, I could call this point here x1 and go like this, and then call this point x2 and go like this. Clearly there is an area there to be calculated which is defined. And yet when I substitute x2 and x1 into my natural logarithm here, it's going to be undefined. Therefore, the answer of just ln x in normal parentheses does not make sense. Therefore, the integral that I have written out here is not valid for x being any real number. This integral I've written out here is actually only valid when x is a positive value, because I can substitute any positive value into my natural logarithm and I will get a result. So I'm just going to adjust this information over here, okay, and I'm going to write x is greater than 0 like that. So we have our result for when x is greater than 0. Now let's think about x is smaller than 0 and try and get the correct answer for this scenario. So I'm going to write out my integral again, which is 1 over x with respect to x. Okay, and what we're going to do is we're going to rewrite our integral before we integrate. What I'm going to do is multiply my numerator by -1 and multiply my denominator by -1. I can do this because all this is doing is finding an equivalent fraction. Okay, our function is still going to be equivalent to 1 over x. So I get the integral of -1 over -x with respect to x. Now let's have a go at actually integrating this. Well, let's consider our denominator and let's differentiate it. So if I differentiate -x with respect to x, I get -1. And that perfectly matches my numerator here. Therefore, my answer to this integral would be the natural logarithm, and then in parentheses I would put -x, my denominator, and then I could write plus, and we'll use d just to indicate that this constant might be different to the one that I've got up here, like that. Okay, so this would be my valid answer for when x is smaller than 0. This would be my valid answer for when x is greater than 0. So essentially there's two answers. However, let's just consider what's going on here. Okay, when x is greater than 0, so positive, we're just putting x in here. Okay, as it is, we're not doing anything with it. However, when x is smaller than 0, when it's negative, we are multiplying our value of x by -1. So essentially, when x is positive, we're not changing it. When x is negative, we're multiplying by -1. Well, what does that remind you of? Well, that's our modulus function. When we have the modulus of x, okay, if x is greater than 0, then our modulus of x is just equal to x. In other words, we do nothing. Whereas if x is smaller than 0, okay, the modulus of x would be equal to -x. Okay, so in this scenario, we'd multiply by -1. So what this allows me to do is to summarize these two results as one single result, where we would write that the integral of 1 over x with respect to x for all real valued x where x is not equal to 0 would be equal to the natural logarithm of the modulus of x plus c. Okay, and that is a complete summary of my two green circled results in one. So we're now going to look at carrying out the reverse chain rule on sine and cosine. But before we get into that, we need to look at some derivatives. So if we have y equals sine x, well, dy by dx is equal to cos x. That is a standard derivative that you need to know. Now, if we have y equals cos x, then dy by dx would be equal to negative sine x. Now, that is another standard derivative you need to know. So it swaps between sine and cosine, but importantly, for cos x, you also multiply by -1 when you differentiate. Now let's consider question 3. Okay, so y equals 3 sine 2x, so dy by dx would be equal to, and when we differentiate sine, we're going to get cosine. We don't need to multiply by -1. The angle 2x will stay the same, and then we will have the initial 3. However, we need to remember to differentiate our angle. So if I differentiate 2x, that gives me 2, and I need to multiply by that 2. So the final answer would be 6 cos 2x, like that. Let's consider the final one. So y equals 4 cos 3x. Well, dy by dx would be equal to, and the cos would become a negative sign. The angle stays the same, so we're going to keep the 3x in there. The initial 4 is still going to be multiplying, so I'm actually going to move this negative sign and make it a -4. And we need to differentiate our angle, which gives us 3, and we need to multiply by 3. So I would get -12 sine 3x as my final answer. So now let's consider some integrals. So I've got the integral of sine x and the integral of cos x. Well, let's look back at our derivatives, because we know that integration is the inverse of differentiation. If I look at my first derivative, my answer was cos x. Okay, so that means if I integrate cos x, the answer should be sine x. Therefore, for the second of these integrals down here, this is going to be equal to sine x, and it's going to be plus c. Okay, I don't need to multiply by -1, because clearly if we look at what happened up here, okay, the sign is staying the same when we're going to the left. Now let's consider our other derivative that we had up here. Well, our answer was a negative sine x. So therefore, if I was to integrate negative sine x, I would get positive cos x. Therefore, if I was to integrate positive sine x, I would get negative cos x as my answer, and then plus c. So when I integrate sine x, we also have to multiply by -1, as well as swapping out the sine for a cosine. So they're the most basic scenarios. Now let's consider the more complicated scenarios, like in question 3 and question 4. Again, we need to figure out how to integrate them. Now to do that, let's consider going from our answers back to our questions. So if we look at our answer here and our answer here and compare them back to our questions. So what is remaining the same? Okay, is anything changing in a specific pattern? Well, in each instance, our angle is staying the same. We got 2x here, we got 2x over there, we got 3x here, we got 3x over there. So what I'm going to say is that our angle stays the same. Now, is there anything that changes in a specific pattern? Well, we have cosine here, whereas we have sine over here. And then we have sine here, whereas we have cosine over here. So clearly, we swap up the cosines and the sines. So I'm going to say swap sine slash cosine, like that. And this is going to be our way into integrating. We're going to make use of this to try and do some integrals. So let's look at our first one then, the integral of sine 3x. Okay, and I'm going to write equals to, and it says the angle stays the same. So therefore, we're still going to have a 3x, because that's our angle here. And then we swap up the sine and cosines. So we got sine here, so we're going to make that cosine. So we end up with cos 3x. So now we have to check as to whether this answer makes sense. We should be able to differentiate it using the chain rule and get back to our initial question. So if we differentiate with respect to x, cos 3x, well, I know that my angle stays the same, so we're still going to have 3x. The cos is going to become a negative sine. And then we also need to differentiate our angle, which gives me 3. And I need to multiply by that. So I'd get actually -3 sine 3x. So if we now do a comparison of what we've got here and our initial question, well, they're not exactly the same. We got sine 3x in each instance, but here we have a -3, whereas up here we have a +1. So the question is, how do I get from -3 to +1? Well, I'd have to multiply by -1/3. So therefore, I'm going to go back to my possible answer and write a -1/3 in front, and of course it should be plus c. And that would be my final answer. So let's have a look at our second one, which looks a little bit more complicated, but let's follow our steps. So the angle stays the same, so 6x subtract 3 is definitely going to be in my answer. Now then to swap the sine and cosines, so this cosine is going to get swapped out for a sine. And then we've got our possible answer, so let's now differentiate this and see what we get. So we're going to differentiate the sine of 6x subtract 3. So when I differentiate, the angle stays the same. The sine is going to become a positive cosine. And then we differentiate our angle, which gives me 6. And I'm going to multiply by it. Now we compare. So if we look at what we've got here and compare it to our initial question, well, we got 6 here. We got 5 over here. So how do I get from 6 to 5? Well, I'd have to multiply by our destination 5 divided by our start point 6. So in front of my possible answer, I'm going to put 5 over 6 to multiply by it, and then plus c like that. So let's have a look at our final one then. So let's go through our steps. Angle stays the same, so pi x is going to be my angle in my final answer. We swap our sine and our cosine, so this is sine, so it's going to become cosine. And that's my possible answer. So now let's differentiate our possible answer. So the derivative with respect to x of cos pi x is going to be equal to, and our angle stays the same, so I'm going to write pi x in. The cos is going to become a negative sine. But we need to remember to differentiate our angle. Remember, pi is a numerical value. So remember, if we differentiate, say, 5x, that just becomes 5. So if we differentiate pi x, well, that's just going to become pi, as that's our coefficient. So therefore, I need to multiply by pi, so I would get negative pi in front like that. Now let's compare what we've got here with our initial question. And in front down here, we've got negative pi. Over here, we got negative 2. So then the question is, how do I get from negative pi to negative 2? Well, as always, I have to take my destination, negative 2, and divide by the negative pi. And that is what I need to multiply by. So that simplifies to 2 over pi. So that is what I'm going to write in front of my possible answer to get my full final answer. And we just need to put a plus c there. Now let's have a think about when we can actually use this method. So this method will only work for one of the following. So let's carry it out and see what happens. Okay, so in our first one here, it says the angle stays the same. So it's going to be 2x squared subtract 6. And then we're going to swap our sines and cosines. So the cosine is going to become a sine like that. Then we're going to differentiate what we've got here. So my angle stays the same, which is 2x squared subtract 6. The sine is going to become positive cosine. And then we differentiate our angle, which gives me 4x, which I'm going to multiply by. Now, if we do our comparison step, we have 4x, lots of the cos 2x squared takes 6. Whereas in the initial question, we have 5x, lots of it. So the question is, how do I get from 4x to 5x, okay, which are the terms written in front of our trig functions? Well, what we'd have to do is multiply by the 5x divided by the 4x. So 5x divided by 4x, well, that simplifies to 5 over 4. Therefore, I'd put a 5 over 4 in front here, and it would be plus c. Now let's see if this answer makes sense, because I should be able to differentiate this using the chain rule and get back to my initial question. Okay, so would differentiating with the chain rule make sense? Yes, it would, because we have our trig function, and it's multiplied by a numerical value. Therefore, the chain rule of differentiation makes sense. So our decision to use the reverse chain rule to integrate to get this answer also makes sense. Therefore, this one here, I can use the reverse chain rule for. Now let's have a look at my next one. So the format of this question is the same, but we now only have a 5 in front as opposed to a 5x. Okay, so I can sort of go through the same initial steps. I know the cosine is going to go to a sine and the angle stays the same. But I know when I differentiate this here, I'm going to get what is written here. So we just have to compare that to our initial question. Well, in front, we have a 4x here, we have a 5 over here. So how do we get from 4x to 5? Well, we'd have to multiply by our destination 5 divided by our start point 4x. Okay, so that's going to go in front of my possible answer. And then, of course, plus c. Now let's consider whether this possible answer makes sense. Well, if I was to go and differentiate this, would I need to use the chain rule? Well, we have a function of x, 5 over 4x, multiplying another function of x here, so therefore we'd have to use the product rule. So this answer would not make sense. Okay, we shouldn't have used the reverse chain rule here. Okay, so for this one, I'm going to put a cross there like that. Let's consider our last one. So once again, it has the same format, so I'm just going to write in the sine of 2x squared subtract 6. And we know that when I differentiate that, we are going to get what is written up here. So we need to compare that to what is written down here. Now, multiplying our trig function, we got 4x, we got 5x squared. So how do I get from 4x to 5x squared? Well, I'd have to do multiply by 5x squared divided by 4x, which simplifies to 5x over 4. And then I'd have to write that in front of my possible answer like this, and it will be plus c. And let's consider whether this makes sense. Okay, if I was to differentiate what's written here, well, we have 5x over 4, a function of x, multiplying another function of x. Therefore, we'd have to use the product rule to get back here, which doesn't make sense given that we use the reverse chain rule to get this answer. We should be using the chain rule to differentiate. Therefore, I should have used the reverse chain rule on this question here. So what we now have to consider is how could we have known that the top one was going to be the successful one just by looking at the questions? Well, if we consider what we did during our steps, okay, we had to differentiate the 2x squared takes 6, which is common to all 3 questions during our steps. And when we differentiated that, we got 4x. And what we need to do is compare this 4x here to what is multiplying our trig functions. Okay, if there is a numerical multiple, then we can use the reverse chain rule. If there isn't a numerical multiple, then we cannot. Okay, so we are comparing the 4x over here to the 5x in the very first question. Okay, the 4x would then be compared to the 5 in the next question, and then the 4x would be compared to the 5x squared in the very bottom one. And if we do our comparison, well, the power of x here is 1, the power of x here is 1. Therefore, we'd have to multiply by numerical value. So that one's a tick, which makes sense, given what I figured out earlier. For the next one, we have x to the power of 1 here. We don't have any x over here, so we'd have to multiply by something involving x, so we can't use the reverse chain rule for that one. And in the final one, we have x to the power of 1 and x squared, so we'd have to multiply by something involving x, so we can't use the reverse chain rule here. Now let's practice using this trick and try and think about the very fastest way of integrating sine and cosine. So in order to figure out the fastest way of integrating sine and cosine, I'm just going to consider one more derivative and clearly write out my steps that I do when I differentiate. So our angle stays the same. So we'd write 2x. I'm just going to note angle stays the same. And then the sine is going to become a cosine. However, if this was initially a cosine, it would become a negative sine. So I'm just going to make a note of that. Okay, so sine becomes cosine, or cosine becomes negative sine, like that. Then I'm just going to write in the 5 so I don't forget about it. And our final step for differentiating is we need to differentiate our angle, which gives me 2, and I need to multiply by that. Okay, so we're going to multiply by the derivative of the angle. So that's our steps for differentiation. Now we need to do the inverse integrate. So let's consider what we need to do. So I've got my steps. Let's write I for integrate. Okay, and let's start with my bottom step and do the inverse. So it says multiply by the derivative of the angle. We're going to divide by the derivative of the angle. Then if we move one step higher, so when we differentiate, sine goes to cosine. Okay, so therefore integrating, cosine is going to go to sine. And for our other scenario, when we differentiate cosine, we get negative sine. Okay, so therefore when we integrate positive sine, it should go to negative cosine. Okay, so for this one, the sign should be changing in front. We should be multiplying by negative 1. Then if we go one step higher, it says angle stays the same. The inverse of staying the same is staying the same. So I'm going to write angle stays the same. Now, none of these steps that I've written here actually influence each other. Therefore, the order in which you do them don't matter. And actually, I would probably concentrate on doing the bottom 2 steps first. Okay, and then do the very final step. So let's have a go at using this. So here's my integral. Let's start by doing our reverse chain rule check. If I differentiate my angle, I get 2. Now we need to compare this value to what is multiplying our cosine function, which is a 1. Are they numerical multiples of each other? Yes, they are. Therefore, we're good to use the reverse chain rule. So let's carry out my steps. So my first step is about picking whether it's sine or cosine and whether it's negative or positive. Well, if I've got cosine, we're looking at our first one here, and that becomes positive sine. Then it says the angle stays the same, so 2x subtract 6, I can write that in. And then we need to divide by the derivative of the angle. Well, I already differentiated it in our reverse chain rule check, and we got 2. So I just need to divide the value in front of the function by 2, so it'd be 1 over 2 like that, and then a plus c. Let's look at our next one. So let's do our reverse chain rule check. If I differentiate my angle, so pi over 6 subtract 2x, well, pi over 6 is a constant, so that differentiates to 0, and negative 2x differentiates to negative 2. Then compare the negative 2 to negative 3. Are they numerical multiples? Yes, they are. So we're good to go. Let's do our steps. So we have cosine in front. Okay, so once again, we are using the first one here, and it's going to be positive sine. So I'm going to write sine in like that. My angle then stays the same, so we're going to write in the pi over 6, subtract 2x. And then we need to divide by the derivative of our angle. So the derivative of the angle was negative 2. So I need to take the initial negative 3, and I need to divide it by the negative 2, and then put plus c. So my final answer is 3 over 2 sine, and then pi over 6, subtract 2x, plus c, like that. Let's have a look at our next one. So let's do our reverse chain rule check. Let's differentiate my angle. So if I differentiate 2x squared, take 3, I get 4x. Well, if I compare the 4x to the half x I've got here, you'd have to multiply by a numerical value because we have x to the power of 1 and x to the power of 1. Therefore, we're good to use the reverse chain rule. So let's carry out my steps. Equals to. Now, this time we have sine. So if we look at my integral options, okay, we're going to use this one here. And the sine goes to a negative cosine. So I'm going to write negative cosine in. The angle then stays the same. So 2x squared, take away 3. We then divide by the derivative of the angle. Okay, so we're going to take the initial half x that was written in front, and we're going to divide by the 4x. So what I'm going to do is just shift this negative sign just to make a bit of space. And I'm going to write in my half x, which I'm going to divide by the 4x. And then we just need to do plus c. Then let's just simplify. If we have a half divided by 4, that gives me an eighth. So we'd have negative an eighth, and the x's will cancel. So we're just left with then the cosine of 2x squared. Take 3, multiply by the negative eighth, and then plus c. Let's have a look at a more challenging question. So let's look at our final scenario involving sine and cosine. So we have sine to the power of 1 multiplied by cosine to the power of 5. Okay, the angles are the same. If the angles were different, it would be far more complicated. Now, what I'm going to do is rewrite this. Okay, I'm going to rewrite it in a slightly different format, which might clear up what we need to do. I'm going to write the sine x in, and then I'm going to open my brackets. I'm going to write cos x, and then I'm going to write the power of 5 outside the bracket like that with respect to x. So all I've done is rewrite things. Usually we use this notation for trig when raising to powers. However, I think for integrating, it might be more useful to write it like I have here. Because now what we've got is essentially a function in a bracket raised to a power. So this goes back to our very first scenario for the reverse chain rule. So then our check as to whether we can use the reverse chain rule in this scenario is to take what is inside my brackets and differentiate it. So if I differentiate cos x, I would get negative sine x, and then we compare this to what is multiplying our bracket and ask ourselves, are they numerical multiples of each other? Well, yes, they are. To get from negative sine x to sine x, I'd have to multiply by negative 1. Therefore, I can use the reverse chain rule, and I need my steps for when we are dealing with brackets raised to a power. Right, so here are my steps. Let's do my integral. So it says the bracket stays the same, so that would be the cos x in here. Okay, that's going to remain exactly the same. It says increase the power of the bracket by 1. So instead of power of 5, we're now going to have power of 6. We're then going to divide by the derivative of the bracket. So I'm going to take the initial sine x here, and we are going to divide it. Okay, and what we're going to divide it by is a derivative of the cos x, which I wrote out over here. So negative sine x. And then we're also going to divide by the power. So I need to divide by 6. So in my denominator, I'm going to do 6 multiplied by the negative sine x like that. And then we need our plus c. Now let's go through and simplify what I've got written here. So my fraction in front, the sine x's cancel. So we're just left with 1 in the numerator, and in the denominator, we'd be left with negative 6. And then we'd have cos x raised to the power of 6 plus c. And writing this in the most simple way, I'd write negative 1/6, and then it would be cos to the power of 6x like that plus c. And that would be my final answer. In terms of what you're looking out for this scenario here, it's when you have either sine or cos raised to the power of 1. So I'm just going to write sine x to the power of 1 and cos x to the power of 1. And then they're multiplied by the other trig function not used yet. So in this case, that would be cosine. And in this case, that would be sine. And the sine and the cosine I just wrote in might be raised to some other integer power. So I'm just going to write n here and n here just to represent that. Okay, so there are two scenarios that you need to be familiar with to integrate because they do come up regularly. We're now going to look at some harder trig questions involving the reciprocal functions and making use of the formula booklet. We're now going to look at how we can integrate trigonometric functions other than sine and cosine using the reverse chain rule and making use of the formula booklet to help us. So I've got the formula booklet here, and we're going to focus first on this left-hand part over here, okay, because this has some crucial integrals that you're going to need to be able to use. So our left-hand column is f of x, that's the function we're trying to integrate, and then the right-hand column is the integral of f of x. Okay, so let's look at our first one. So our first one is for sec squared in particular, so not sec cubed or sec to the power of 1, it's for sec squared specifically. And the result of our integral is tan. Okay, as you can see, just as before with sine and cosine, our angle, which is kx, stays the same throughout. And then also, we have this 1 over k. In terms of what that represents, well, if we went to our angle, kx, and we differentiated it, we would get k. Well, the 1 over k represents us dividing by k. Okay, so we still got that same step of dividing by the derivative of the angle. Let's have a look at our next integral. So our next one is for tan to the power of 1, and this integrates to ln and then sec in the modulus symbols. And as always, and this will be the case for all of the integrals we're going to do, the angle will definitely stay the same, so kx and kx. And as usual, we will divide by the derivative of our angle. Now, I am just going to talk about where this integral actually comes from. So if you were asked to integrate tan x with respect to x, you would start by rewriting tan x using an identity. I would write it as sine x over cos x. And then we've got a fraction. The denominator is raised to the power of 1, so we're not going to want to rewrite it using indice laws because then we'd get a negative 1 power. So what we want to consider instead is, can we use the natural logarithm? Okay, if I take my denominator, which is the cosine of x, okay, if I was to differentiate the cosine of x, well, that would give me negative sine x. And then what we do is compare this negative sine x I've got here to my numerator and ask ourselves, are they numerical multiples of each other? Well, yes, I'd have to multiply by negative 1. So we could use the reverse chain rule with the natural logarithm. So our answer would be the natural logarithm of the modulus of our denominator, which was the cos x, and then we'd have to multiply by negative 1, which is what we found down here. Then we'd add our plus c. However, as you'll see, this doesn't match the integral that we've got over here, okay, because we end up with sec. So where is the sec going to come from? Well, we're going to have to use the laws of logarithms. If we have a negative 1 multiplying our logarithm, we can bring it in as a power. So this here is going to be equal to the natural logarithm of the modulus of cos x raised to the power of negative 1 and then plus c. And if you have cos x raised to the power of negative 1, well, that is the reciprocal of cos x. Okay, so that is going to be sec x. So I can write sec x in, and now we match the integral given in the formula booklet. Now, just be careful with this. You see how I've written the power of negative 1? You have to write it like that in brackets. Okay, you can't put it over here because that means the inverse function, which is something different. Let's have a look at my next integral. So our next one is for cot to the power of 1, and you can see it integrates to ln and then sine in the modulus symbols, and once again angle stays the same and we divide by the derivative of the angle. So I'm going to explain where this one comes from. If we were to integrate cot x with respect to x, I would rewrite cot using the fact that cot is 1 over tan, and we said that tan is sine over cos, therefore cot would be cos over sine. So I'm going to rewrite it like that. And then once again, we're going to consider, can we use the natural logarithm and the reverse chain rule? Well, we'd have to go to my denominator, which is sine x, and we would have to differentiate it. So if I differentiate sine x, well, that gives me cos x, and that is a perfect match of my numerator. My numerator is cos x, so therefore we can use the natural logarithm, and our answer is going to be the natural logarithm of our denominator, which was sine x in modulus symbols. And we wouldn't have to multiply by anything other than 1. Okay, so I'm going to leave that blank, and it would just be plus c, which perfectly matches my integral over here. Let's have a look at our next ones. So our next two are for cosec raised to the power of 1 and sec raised to the power of 1. And you can see they both come out using the natural logarithm, and they have different trig functions inside there being added together. Now, don't worry about where these two come from. Actually, these two don't pop up particularly regularly, but you might have to potentially use them, and you've got the integrals here. So that's the first part of the formula booklet discussed. We now need to discuss what is written over here, okay? Because this is actually the information for differentiation, because we have f of x in our left-hand column, and then we have f dash of x over here. So we are differentiating, I'm going to represent that with a d, going to the right. However, remember, every time you differentiate, you get an integral. Okay, if we start with the right-hand column, our f dash of x, well, if we were to go in the opposite direction, so to the left, well, then we're integrating, which I'm going to represent with an I. So let's look in my right-hand column. Okay, in our right-hand column here, we have sec squared. So therefore, we know that the integral of sec squared x with respect to x would be equal to what we got in our left-hand column, which is tan. Okay, so it's tan x and then plus c. Now, that one's not particularly interesting because that's what we had in the top integral over here. However, this does explain where this integral comes from, okay, because you should have practiced previously differentiating tan using the quotient rule to get sec squared, and then subsequently, if you know that derivative, well, then you know the integral of sec squared is going to be tan. Now, let's look at my other three, which are a bit more interesting, as these other three are not provided in my integration part of the formula booklet over here. Okay, so if we take a look at the second one, well, we have sec x tan x over here. So what we can determine is that sec x tan x integrated is going to be equal to what we got in the left-hand column, which is just sec x. And then, of course, plus c. So this is for where we have sec raised to the power of 1 multiplied by tan raised to the power of 1. And importantly, our angles are the same. If the angles are different, you're going to have to rewrite it first to make them the same before you can attempt to use any of these integrals that I'm about to talk through. Now let's look at my next one. So in my next one, if we look at the right-hand column, we have cosec squared. Okay, so we're going to write the integral of cosec squared x with respect to x, and that's going to be equal to, and we've got cot over here. So I'm going to write in cot x, and the cot's to the power of 1. However, there is something else we need to add, because in my right-hand column, we have a negative symbol here, whereas down here, I have kept it as positive. Therefore, we need to multiply our answer by negative 1. So it's actually going to be negative cot, and then we'll put the plus c like that. Let's have a look at my last one then. So my very final one involves, in the right-hand column, cosec being multiplied by cot. So we're considering the integral of cosec to the power of 1 being multiplied by cot to the power of 1 with respect to x. Now let's look at what we get when we actually integrate that. Well, we get cosec raised to the power of 1. And then plus c. However, once again, we just need to be careful because there is a negative symbol here, whereas in the integral I'm doing down here, we've kept it positive. So we're going to have to multiply our answer by negative 1. So I'm going to have to put a negative 1 in front of my cosec x to get my complete integral. So we can use all the information here using the reverse chain rule as we've been practicing for sine and cosine in the exact same way. However, just one important note, this is the formula booklet for Edexcel. If you do OCR, then you're only going to get the bit that's circled in red. Okay, you won't get the other bits. However, that means you're going to have to logically be able to come up with these two integrals here in particular, like we've discussed. And don't worry about the bottom two, okay, because they just won't come up in OCR. Now let's have a go at actually using this to carry out some integrals. So we've got our integral here, which is cot 4x, and I've got the formula booklet, and I've also got my steps for doing the reverse chain rule with trig functions. Now I have made one addition. Okay, previously we've been focusing on cos to sine and sine to negative cos, but I've also got formula booklet written here as we might need to revert to that, and actually these questions we're mainly going to be using the formula booklet. So let's do our check as to whether we can use the reverse chain rule. We're going to go to our angle 4x, we're going to differentiate it, which gives me 4, and then we're going to compare that to the number multiplying my trig function, which is a 1. Well, to get from 4 to 1, you have to multiply by a numerical value. Yes, you do. So therefore, we can use the reverse chain rule. So let's have a go at actually carrying out my steps. So I'm going to write equals to, and then I need to figure out where is cot raised to the power of 1 in my formula booklet. Well, if we look at my integrals, I believe it is here. Okay, the integral of cot is ln of the modulus of sine. And remember, the angle stays the same throughout. We have to divide by the derivative of the angle as usual. So let's carry out my steps written here. Okay, using the formula booklet then, we know in my answer it's going to be the natural logarithm of the modulus of, and it's going to be sine, and the angle stays the same, so it's going to be 4x, and then I'm going to write in my plus c. What I just need to remember to do is to differentiate my angle, which gives me the 4, and I must divide by this 4. Okay, so we're going to take the initial 1 in front of the cot function, and we're going to divide by 4, and that's going to be my final answer. Let's have a look at another one. So here's our next integral. We have cosec being multiplied by cot. Importantly, our angles are 2x in both cases. Okay, that's going to be important when we've got trig functions multiplied together if we're going to be able to integrate. Let's do our reverse chain rule check. Okay, we're going to take my angle 2x and we're going to differentiate it, which gives me 2. Then we're going to compare this 2 to the 3, multiplying our function. Are they numerical multiples of each other? Yes, they are. So we can use the reverse chain rule. So now let's go and look at my formula booklet. Where is cosec being multiplied by cot? Well, if we look at our integrals given here, okay, cosec being multiplied by cot doesn't seem to be represented. However, if we go and look at my derivatives over here, you'll see in my right-hand column, which is what we should be focusing on initially, we have cosec being multiplied by cot down here. And that integrates to a function involving cosec. Okay, so let's start writing things out then. Okay, so when we integrate the cosec multiplied by cot, we're definitely going to have cosec in my answer. But just be careful because we have a negative symbol here in the formula booklet, whereas at the start it's positive. So therefore we're going to have to multiply by -1. So I'm going to put negative cosec in. Okay, our angle stays the same. So I'm going to write in my 2x like that. And now we're on our final step, which is dividing by the derivative of the angle. Okay, if we differentiate the angle, we know we get 2, which is written up here. So we just have to divide by 2. Just remember to bring down our 3. Okay, so it's going to become negative, and then it's going to be 3 over 2, and it would be plus c like that. Let's have a look at another one. So let's look at our integral, and this one's a bit more complicated because we now have sec raised to the power of 4. If you look in your formula booklet, you don't have sec raised to the power of 4 anywhere there. So currently, as it's written, it doesn't seem that favourable to use the formula booklet. Well, let's consider rewriting my sec to the power of 4x. What I'm going to do, I'm going to rewrite it by putting the sec x in brackets and putting the power of 4 outside like that, and then tan x. And that's my integral that I'm going to have to do in this case. So essentially the scenario I've ended up with is a function in a bracket raised to a power being multiplied by something. Okay, so we're going to have to consider our reverse chain rule check for when we were integrating brackets raised to a power. So what I do is I take what's inside my bracket to be sec x, and we need to differentiate that. So what do I get when I differentiate sec x? Well, if I look at my formula booklet and look at my derivatives, okay, we're differentiating sec x over here, and we get sec tan. Okay, so we're going to write out our derivative, which is sec x, and then tan x, like that. Now let's compare this derivative that we've got here to what is multiplying our brackets, which is just tan x. How do I get from sec x tan x to just tan x? Well, you'd have to divide by sec x, or you could write it as multiplying by 1 over sec x. Okay, because usually we write in terms of multiplication when we're doing this. Now that is not a numerical value. Therefore, as it's currently written, I cannot make use of the reverse chain rule. So I'm going to consider how I can rewrite the integral further. Okay, because we want, ideally, a numerical multiple of sec x tan x outside the brackets. But currently, we only have tan x. So how am I going to magically get a sec x out there? Well, I can make use of the fact that in my question, I have sec x raised to the power of 4, and I can pull out a factor of sec x from that. So let's rewrite the integral again. So what I'm going to write is my integral symbol, and then I'm going to write sec x, but I'm going to raise it to the power of 3, because I'm going to pull out a factor of sec x, which I'm going to write outside the bracket like this, and then tan x, and then with respect to x. Now if we go and differentiate, okay, what is inside my bracket, I would get sec x, tan x, which now perfectly matches with what is written outside my bracket, which is multiplying it. Okay, therefore we can now use the reverse chain rule because they're numerical multiples of each other. Okay, so let's carry out our process for the reverse chain rule when we have a bracket raised to a power. So I've got my steps for doing the reverse chain rule with brackets raised to a power here. Let's carry them out. So it says the bracket stays the same, so therefore the sec x inside my brackets is definitely going to be in my answer. It says we increase the power of the bracket by 1, so we've got a power of 3 up here, so therefore it's going to become a power of 4. Then it says divide by the derivative of the bracket. So what I'm going to first do is just carry down the sec x tan x multiplying the bracket. So I'm going to write in sec x tan x. And then I'm going to divide by the derivative of the bracket, which is what we found here, which is also sec x tan x. But then we have one final step to do. We need to divide by the power. So our new power is 4. So that 4 is going to multiply into the denominator over here. So we get this. And of course, it should be plus c. And then what we need to do is simplify what's written there. Okay, so the sec x raised to the power of 4 can become sec to the power of 4x. And that's going to be multiplied by, well, the sec x tan x in the numerator cancels with the sec x tan x in the denominator. So we're just left with 1 over 4, which I'm going to write in front for neatness. And then we've got our plus c. And that would be my final answer. Let's have a look at another one. So we got our integral here. And this one looks a bit more complicated as we've got a fraction involving trig functions. Now what I note is that the denominator is raised to the power of 3. Therefore, what I'm going to do is I'm going to rewrite this with indices laws. Okay, I'm going to write equals to our integral symbol. We'll write our numerator, which is the cosec squared 2x. And then we're going to open brackets, write in the bracket from my denominator, so 2 plus cot 2x. However, it's going to be raised to the power of negative 3 instead. Okay, so I've written it in this format, and what we've essentially got is a function written in my brackets, raised to a power, being multiplied by something else. So I've got my steps for integrating when we have functions raised to a power down here in brackets. Okay, so what we're now going to do is do our check for the reverse chain rule. So what I'm going to do is differentiate what is inside my brackets here and see what I get. Well, when I differentiate 2, that's a constant, so that becomes 0. So I'm just going to have to concentrate on the cot 2x. Well, if I look at my derivatives over here, cot to the power of 1 is here, and it differentiates to negative cosec squared. Okay, so I know when I do this derivative, I'm going to get negative cosec squared. The angle stays the same, so it's going to be 2x. But I also need to differentiate my angle, which gives me 2, and I need to multiply by it. So I'd actually get a negative 2 in front instead. Now, if we compare that to what is written in front of our brackets over here, you can see they are numerical multiples of each other. They've both got cosec squared 2x, okay, and they're both multiplied by numerical values otherwise. So they're numerical multiples, so we can do our reverse chain rule. So let's carry out my steps. So I'm going to write equals to, and it says bracket stays the same. So I'm going to write 2 plus cot 2x, okay, close bracket, but the power increases by 1, so it's going to become negative 3 to negative 2. Then we need to divide by the derivative of the bracket. So I'm going to take what was initially multiplying our bracket, the cosec squared 2x, and I'm going to divide by the derivative of my bracket, which we wrote up here. Okay, so that is the negative 2 cosec squared 2x. Okay, so in my denominator, I'm going to write negative 2 cosec squared 2x. However, my other step that I have to do is to divide by the power. So I'm going to divide by negative 2. So we'd have a negative 2 multiplying into my denominator. And then, of course, we got plus c. Now, let's simplify what's written there. Well, the cosec squared 2x is going to cancel with the cosec squared 2x down here because they're factors of the numerator and denominator. So I'm left with 1 divided by negative 2 times negative 2, which is positive 4. And then I'd have my bracket 2 plus cot 2x raised to the power of negative 2 plus c. And that would be my final answer. Let's look at another one. So we have another fraction, but this one's a bit different because the denominator is raised to the power of 1. So we're not going to want to use indices laws because then we're going to get a negative 1 power, which we don't want for integration. So what I'm going to have to consider is whether I can use the natural logarithm. So let's do our check. Let's take my denominator and we're going to differentiate it. So if I differentiate tan 2x plus 1, well, the plus 1 is a constant, so that becomes 0. As for the tan 2x, let's look at my derivatives. And it's the top one here. Okay, it differentiates to sec squared. Okay, so my derivative would be sec squared and it's going to be 2x because the angle stays the same, but differentiate your angle, which gives me 2, and I need to multiply by it. Now compare this to our numerator. Are they numerical multiples? Well, yes, they are. To get to my numerator, I'd have to multiply by 1/2. So let's now use the reverse chain rule with the natural logarithm. So it's going to be the natural logarithm of the modulus of my denominator. So that is the tan 2x plus 1. And then we're going to close our modulus. We'll put our plus c, but just remember we also need to multiply by 1/2. So I'm going to have a half written here like that. And that would be my final answer. Let's have a look at another one. So here's our next integral. Looks pretty complicated. This one actually involves e. So I've got my steps for integrating e written at the bottom here. But let's do my reverse chain rule check first. Okay, we go to our power 2 cot 2x. And we're going to have to start by differentiating that. Okay, so in my derivatives, where is cot? It is here. And when we differentiate that, we get negative cosec squared. Okay, so I'm going to write my negative cosec squared. And the angle stays the same, so it's going to be 2x. So let's then differentiate my angle of 2x, which gives me 2, which I'm going to have to multiply by. But also don't forget about this 2 here, okay, which I'm going to write in. And then we're also going to multiply by the 2, which is the derivative of the angle, which would give me negative 4, and then it will be cosec squared 2x. Now let's compare this derivative here with what is multiplying my e function, and they are numerical multiples of each other. They both have cosec squared 2x and are multiplied by a numerical value. So let's use our reverse chain rule steps for e. So it says that our base e stays the same, so I can write equals 2, and I'm going to write in my e. And then it says the power stays the same, so it's going to be 2 cot 2x. And then it says divide by the derivative of the power. Okay, so I'm going to take what's initially multiplying my e function, so v3, and it's cosec squared 2x. And I'm going to divide by the derivative of my power, which is written up here. So that is the negative 4 cosec squared 2x, like that. And then it's plus c. Then the final thing I need to do is simplify that fraction, because it has a common factor of cosec squared 2x, so those cancel, and then we're just left with negative 3 over 4 e to the 2 cot 2x, and then it's plus c. And that would be my final answer.